So we discussed last time the case of natural convection or free convection, and we have seen that it will be affected by several parameters, including the geometry of the surface, the roughness of the surface, the type of fluid over the surface, etc. Okay? Now, and we said that we need to develop some empirical relations to find the convective coefficient H. And we discussed that Nusselt number is a dimensionless number that will allow us to calculate H. Today we'll do problems to understand better in a better way this idea. Let us consider, for example, the case of a long horizontal cylinder. So if we, for a heated cylinder, the local Nusselt, when we say local, it means that we are finding it at a certain position. And if I consider, for example, the following figure, okay? What is happening is that the temperature of the cylinder is much larger than the ambient temperature. Because of this, what will happen is that air at the vicinity of the cylinder will be heated. And because air at the vicinity of the cylinder will be heated, then what will happen is that air will be entrained, okay, and will move over the cylinder because you have that the density is lower here, so air will tend to move up, okay, and this will form a boundary layer around the cylinder, and it's an ascending plume here. It's an ascending plume because you have T surface larger than T infinity. If you have the opposite, if the temperature of at ambient condition is larger, then the maximum temperature of air will be at this level, okay? And because of cooling effects, since the surface of the cylinder is at lower temperature, because of cooling, air will flow in the opposite way. Since particles at the vicinity of the cylinder will be at a lower temperature, so higher density, and then whenever you have particles of high densities, they tend to move down. Okay, so in case you have the opposite scenario, you will have downward motion of air instead of upward motion of air. Now, if you want to calculate, for example, the total heat transfer between the cylinder and the ambient air, we can say that in overall, Q is equal to H average. You know, the convective coefficient might change with location, okay? Yani the convective coefficient here is different than its value here because you have the boundary layer thickness is not the same everywhere, okay? That's why we define like an average value of H over the whole area. So you can say that total loss is Q equal to H bar average times area times
دكتور
delta T.
بس فينا نعيد بارت الافريج.
أكيد. Okay. Anna, for example, I can ask you two types of questions. I can tell you at this location here, for example, at theta 90 degrees, okay? This is theta 0. This is theta equal 0, okay? I can ask you for theta equal pi over 2, yani at this location here. What is H? If I ask you this when I specify a location, you tell me I need to determine the Nusselt number at this location, theta, at 90 degrees, okay? It will be different than the Nusselt number, for example, at 180. Because look, here the boundary layer here is different than the boundary layer thickness here, okay? And this will affect the value of Nusselt number, and you can find this experimentally. And experimentally, you can determine Nusselt number at different locations, at different angles. And since Nusselt number is by definition H, which is the convective coefficient at a certain angle theta, okay? So Nusselt at theta is equal to H at theta times characteristic length of my geometry, okay, over K, conductivity of my material. So Since Nusselt will vary with location, H also will vary with location. So for any angle I ask you about, you can say that the convective coefficient for this angle, okay, is equal to Nusselt for this angle times K over L. Okay. So in this way, you can determine at each position what is H. But actually, to find the total heat transfer, you need an average value. And if I ask you find the total heat transfer over the cylinder, if I just ask you find the heat transfer rate at one location, and in what per meter square, if I ask you at this location, what is Q second? You say Q second at this location, at this theta, okay, is equal to H at this theta times delta T, okay? But actually, whenever you want to calculate the total heat transfer, you need to consider summation. Yani for this small area, I will call it dA, okay? Elementary area. For this elementary area, you multiply by H theta delta T. If you take another area, H will be different, etc. You do integration if you want, integral to find Q second dA in order to find the total rate Q, okay? And if you do this, you can say, I can define like an average heat transfer coefficient. So after I do integration and find total Q, I say, I can define like an average value of H in a way that Q is calculated as H average times area times delta T, okay? And to not have to do the integration, we define an average value of the convective coefficient. Clear? For the one who asks the question, is it?
Yes.
Clear?
Yes.
Okay.
Yes.
Okay. And then you can say that H average is equal to Nusselt average okay, times K over L. Okay, this is why we'll see now in coming slides that when they give formulas, they give formula for local Nusselt. So if you are interested in the flux at a certain location, you use local value. If you are interested to get the total heat rate loss, you use the average value of H. Okay. So going back to this example, as we said, if we have the temperature of the cylinder larger than the ambient temperature, then we can say that the maximum temperature will be at the bottom and it will decrease for larger value of theta. Okay, so the boundary layer development will begin at theta equals 0 and will conclude at theta equal pi, and at this level when we do a complete turn over the cylinder. Okay, so this is theta 0 here, and this is theta equal pi if I turn 180 degrees. Okay, I have at different locations different values of Nusselt. Now let us do some analysis. While Nusselt is maximum at 0, because you have the maximum temperature difference at this level. Here you have a very thin boundary layer. So the variation of temperature will take place in a very thin, small thickness, and this will correspond to a high value of Nusselt. And as you turn towards theta equal pi, the thickness of your boundary will increase, and this will lead to a reduction in Nusselt number. So Nusselt number is maximum at 0 and minimum at 180. That's why H also, the convective coefficient H, will be maximum at 0 and minimum at pi. Okay? So now what if we have the opposite scenario? So if the cylinder is cooled relative to the ambient fluid, just the flow will be opposed. So boundary layer development will begin at this point, and it will begin at theta equal pi. And here the local Nusselt will be maximum. And then the plume will descend downward, and the minimum Nusselt number will be at theta equals 0 here. Okay? Now, as we said, for different geometries, we have different values, different empirical relations. For example, here, I consider if I have a sphere, okay, they gave us here the average Nusselt number. We have also formulas for local Nusselt number. So if you are interested into the overall heat transfer rate, you need the average Nusselt. And this average Nusselt number is depending, of course, on Rayleigh and Prandtl number. And as we discussed before, for each formula, I give you a valid range. Okay? So you should be within this range to apply the formula.
دكتور
Now,
من اول ما بلشنا بهالشابتر لهلا كل شوي بيطلع لنا فورمولا وارقام وكذا، هول شو نعرف فيهم؟ نحفظهم؟
no, of course no. All of these formulas will be given to you. Okay? You just, when we do problems, you will learn how to use them. Look, we said that H vary with the geometry and with the fluid. Okay? So when I give you the geometry, and if you have a sphere, for example, you go to formulas for a sphere. You say, I will use empirical relations for a sphere. If you have a cylinder, a horizontal one, you use this graph, etc. You don't have to memorize anything. You just need to know how to use these formulas or how to use these graphs. And now in problems, we'll see how to use them. Okay? You don't
دكتور I have a
memorize.
question.
Yes.
بالأول قلتي لنا أنت شيء إنه Rayleigh's number is equivalent to Reynolds under shear condition.
Yes. In case of natural convection. In free convection, can you mute please your microphone? Okay. Look, whenever you have a natural convection, okay, instead of dealing with Reynolds number, you deal with Rayleigh number. And you calculate Rayleigh. And Rayleigh number will allow you to know if your flow is laminar or turbulent, and then will allow you to, depending on the range your Rayleigh number is, to select the appropriate formula to use. Okay? We'll see this when we do problems. This will be much clearer for you. Okay? We'll start now with problems.
Okay, thank you.
I will start with problems so you can understand it in a better way. Example. Air flows through a long rectangular heating duct that is 0.75 meters wide and 0.3 meters high, and this duct is maintains the outer duct surface at 45 degrees. If the duct is not insulated and exposed to air at 15 degrees, what is the heat loss from the duct per meter of length? Okay, so first, what we should do a small sketch. We should do a small sketch to be able to do the analysis. So this is our duct. Okay, we have its dimension. The height of the duct is 0.3 meters. We have the width is 0.75 meters. We have flow moving in the duct, okay, and they said it's a very long duct. Now the air at the outer side, the temperature of air is 15 degrees, okay, and the surface temperature of our duct is 45 degrees. The question is to determine the heat loss from the duct per meter of length. Okay, so if I have 1 meter of length, what will be the heat loss? Okay, let us do some analysis together. In this problem, okay, what do we have? We have several surfaces. We have some surfaces that are vertical and other surfaces that are horizontal. Okay, so we need to calculate the total heat loss. We need to consider the heat loss from each surface and add them together. Okay, now they told us in the given that because of the airflow through the duct, the outer duct surface is maintained at 45 degrees. So we are in a case where T surface is given. It's equal to 45 degrees. Okay. And T infinity is also given. T infinity is 15 degrees. Okay. And we know the geometry of our duct. Here the duct is a little bit complex. Why? Because how many surfaces are doing exchange with the surrounding? You have, this is the top surface. It will exchange heat with the surrounding. This is the bottom surface. Okay, and you have two lateral surfaces that are vertical. So this is surface one. So here, this one and this one are two vertical surfaces. So if I want to find total heat loss per meter, because they said per meter, yani what is the length here? 1 meter. Okay, so I want to calculate Q prime in watt per meter, which correspond to a length here of 1 meter. Okay, what can I say? I can say that Q prime is equal to Q prime from top plus Q prime from bottom. Okay, plus 2 times Q prime vertical. Can you tell me why for top and bottom I don't have the same loss?
لأنه فوق في اير تحت ما في اير.
بلا في air فوق وتحت. بس look, to be able to answer this question, let us go to the previous slides to see which cases we will use in our problem. Okay, look, we have a vertical surface and horizontal surface. Okay, so first, for horizontal surfaces, we have seen this together last time. Look at this graph. And you have two horizontal surface. Top, and you have your duct. At the top level, okay, air is above the surface. So the surrounding air is above the surface for the case of top face. Okay, so I am in which scenario here? If I have A, B, C, D, you remember what is the difference? We said that for A and B, we have T surface yes, here you have when the flow, yes, for A and B, the flow is moving downward, yani T surface is smaller than T infinity. When you have a downward motion, this means that the surface is cooler than air, okay? While for cases C and D, you have hot surface. So C and D correspond to case of hot surface, while A and B correspond to the case of cold surface. Okay? Now, For each case, also we have two scenarios. We have the scenario of fluid above. So this is called, for part C, you have fluid above hot surface. And here you have the fluid. The fluid here is above. Okay. And here the fluid is below. Fluid is below. Okay. Here in the names, they considered, instead of talking about the fluid, they talked about the surface. So if the fluid is above, when the fluid is above the surface, okay, we can say that the top surface is exposed to the fluid. So C is top surface of hot plate. While in configuration D, because the fluid is below surface, then the bottom surface will be in contact with the fluid. So case D is called bottom surface of hot plate. Okay? And in our problem, we are in these two cases, C and D. For the surface at top, okay, we have case C, top surface of hot plate. While for the bottom surface, we are in case D. And cases C and D will not have the same formulas for Nusselt. Now we'll see in the next slide. Okay, so first you should detect in which case you are. You have a top surface which corresponds to case C, top surface of hot plate, and the bottom surface corresponds to bottom surface of hot plate. And if you go to the next slide, they will give you the formulas. They tell you if you have, first you are in the case of isothermal surface, yani temperature of surface is fixed, which is your case in this problem, okay? They said here for horizontal plates of variable shape. So here, it doesn't matter the shape, yani if it's a rectangle or triangle, we don't care. We care that it's positioned in horizontal, in the horizontal position. So for horizontal plates of variable shapes, it can be, for example, a square, a rectangle, a circle, etc. So whatever shape, the formula will apply, okay? But we need to define a certain characteristic length. What is the characteristic length in this case? This characteristic length, we will use it in Nusselt and Rayleigh number calculation. And to find the characteristic length, all we have to do is to consider the area of the surface over the perimeter of the surface. Yani for example, here you have, for the top and bottom plates, you have the same characteristic lengths because they have the same dimensions, but you don't have same Nusselt because, well, when we will see now, the formula to use for upper surface of hot plate, these are the formulas that you can use depending on the value of Rayleigh. And we should calculate Rayleigh, then depending on the value of Rayleigh, or we use this formula or we use this one. Okay, for the upper plate, you have the choice between these two empirical relations. To know which one to use, you calculate Rayleigh number. If Rayleigh that you calculate is between 10.4 and 10.7, and Prandtl number larger than 0.7, you use this formula. If you get Rayleigh number larger than 10 to the power 7, whatever is Prandtl number, you use this formula. This is for the upper plate. While for the lower plate, you have this formula to use, okay? So Rayleigh should be in this range. If Rayleigh is not in this range, you need additional correlations. So I will give you more formulas and you select the one corresponding to the range of Rayleigh in your problem. We'll see how to calculate Rayleigh and how to select the appropriate relation. But to calculate Rayleigh, we need L, because as you can see, Rayleigh at L. You need L. What will be L in this case for a rectangular shape? Okay, we said we are considering 1 meter. And we have the width. Okay, we have the width, W. Okay, so the area will be W times 1. And the perimeter will be 2W plus 2 times 1. Okay. Now, what do we have also? We have the two vertical surfaces. So this is for the top and bottom. We'll get the relations from here. While for the vertical surfaces, we need to go to the case of isothermal vertical surface. Okay? So for isothermal vertical surface, this is the slide corresponding to isothermal vertical surface. The characteristic length is the height. Okay, it's the height of the vertical surface. So here, the two surfaces have same height, same geometry, and we don't have two different cases. We don't have top and bottom, so the formula will be the same for both. Okay, so we can get the value of Rayleigh and verify. This is one possible relation to use. In case Rayleigh is larger than 10 to the power 9, we can use this relation. If not, we can try to find we investigate the relations given, and depending on the empirical relations that will satisfy the conditions, we select it. Okay. So for example, for a vertical plate, you have several choices. You have, for example, depending on the value of Rayleigh, if Rayleigh is smaller than 10.9, you can use this. Okay, while you have this formula is general, and for that it will work for all Rayleigh number. So in case you didn't find a formula for your, if Rayleigh is not smaller than 10.9, and also it's not satisfying the conditions that we have seen in this slide. Okay, here it will be or smaller or larger than 10.9, and you can use, if larger than 10.9, it's good to use this one. If smaller than 10.9, you can use this one. But also you have a more general relation that can work for any Rayleigh number, which is this formula. But in general, we prefer to use specific relations because when you have a relation that is more specific, it will be in general more accurate. Okay. So now let us go back to our problem to see how we will apply these formulas to our problem. Okay, so first, as we said, we need to divide the analysis. We need to consider the vertical sides, okay, and the horizontal top and bottom sides. So first, we said, what is the first approach to do? The first approach to do is to calculate the Rayleigh number. And also, I give you formulas for Rayleigh. You don't have to memorize anything in this chapter. Just need to know how to apply the methodology. Okay, so first, what you should do, you go to your appendix, you find what is formula of Rayleigh number. The formula of Rayleigh number is G, which is the gravitational acceleration, 9.8 meter per second square. Beta, here we should pay attention for something. Okay, we need to determine properties beta, mu, alpha. All of these properties depends on the temperature. Okay, depends on the temperature. But here we have two temperatures. We have you have the temperature of the surface, which is 45 degrees, and you have T infinity, which is 15 degrees. We should take, like, if you want, a representative temperature. And if you go back to your relations, they will tell you which temperature to use. And for example, here, they tell you should use for this empirical relation, all properties are evaluated at film temperature. Okay? So when you go to your relations, they will tell you at what temperature to evaluate properties. In general, most of the correlation will use the film temperature as reference temperature, but sometimes it's not the case. So always verify when you want to use a certain Nusselt number formula. Verify as they should put for you in these conditions, what is the temperature used. So according to our slides, the temperature used for, in this case, for vertical and horizontal case, for both cases, the reference temperature is the film temperature, which is Ts plus T infinity over 2. Okay, so here, for example, in our case, we have the surface temperature is 45. The ambient temperature is 15. So we take the average, which is 30 degrees. Okay, so now I get T film. This is called the film temperature. It's 30 degrees. So I need to evaluate all the properties of my fluid at 30. My fluid here is air. Okay, so I should go to the table. I will show you tables. You have tables posted already in the appendix. We'll discuss them together. You go to the table, you open, for example, here you have table A4 for air. This table will give you for each temperature all the properties you want. It will give you the kinematic viscosity, the value of alpha, the value of conductivity. Now for beta, no need for the table because we can deal with air as an ideal gas. And for an ideal gas, beta is calculated as 1 over the temperature. But please pay attention. Your temperature T should be in Kelvin, not in degrees. Okay. So here, for example, if 30 degrees, yani 303 Kelvin, you do 1 over 303, you get the value of beta. Okay. And also you can read from your table the value of a Prandtl number. And we have already seen that what is Prandtl number? It's the ratio of mu over alpha. So if you divide mu by alpha, you will get Prandtl number. Okay. So now we have all properties from table for the film temperature. Now we are ready to calculate Rayleigh number. Okay. Because Rayleigh number is G, which is 9.8, times beta, which is 1 over temperature, times T surface minus T infinity is 45 minus 15, it's 30. Now, what about the characteristic lengths? Okay, the characteristic lengths will vary depending on the surface. We said that for the vertical surface, if you go back to the slide of vertical surface, they tell you in case of a vertical surface, the reference, the characteristic length is the height. I just consider the height. So please pay attention. The Rayleigh number is not the same for all surfaces because the characteristic lengths L will vary from horizontal to vertical surface. For vertical surface, I replace the characteristic lengths by the height, which is 0.3. And then I get my Rayleigh number. I get a Rayleigh number equal to 7.07 times 10 to the power 7. So this is smaller than 10 to the power 9. So I should go to my slides of vertical surface and select the Nusselt relation that is applicable for Rayleigh number smaller than smaller than 10 to the power 9, which is, we'll go and search for it, which is this relation. Okay, so you can apply this relation here. It's not your only choice. You have several choices, but since here you have a value smaller than 10 to the power 9, and you can verify that the Prandtl number is in the range required, you can use this formula. Okay, now all you have to do is to replace. You have your Rayleigh, you replace it. You have your Prandtl number here. They said they calculated Prandtl at 0.71. You replace it. Okay, once you replace, you get Nusselt. You get Nusselt average. Okay, and you say, by definition, what is Nusselt? Nusselt average is equal to H average times characteristic lengths, L characteristic. What is the characteristic lengths here we said for the vertical surface? For the vertical surface, the characteristic length is the height, 0.3. So I replace L characteristic by 0.3. Okay, over conductivity K. You have the characteristic length, which is the height. You have the conductivity from the properties of air at this temperature. You have calculated now according to the empirical relation, you calculated Nusselt. Now you are ready to calculate H bar. And this coefficient h bar is for what? It's for the vertical sides. So this is for the vertical sides. Okay. Now, just to remind you how we got this formula, we calculated Rayleigh. We should go to the slides of vertical surface and see this Rayleigh correspond and Prandtl given correspond to which range. So since it's 7 times 10 to the power 7, if you go to the previous slides for vertical case, okay, so you have several formulas, okay, for a vertical plate. So you look, do I have Rayleigh larger than 10 to the power 9? No, I cannot use this formula. I continue to move down. I have here two relations. One that is applicable for all Rayleigh numbers, okay? But in general, whenever, as we said, if I have a specific value, it will be better. Since this relation is applicable for Rayleigh smaller than 10 to the power 9, which is my case, I will select this relation. So for this relation, the condition is satisfied and it's more specific. I can use it, okay? Now, I say in this formula, the characteristic lengths L, how I know it, I go back to the previous slide. They tell me that whenever you have a vertical surface, take the height as characteristic lengths. It should be mentioned somewhere here. Okay. So if not mentioned here, in general, you should have it in the table. In the table, they tell you what is the characteristic length. Okay. So for a vertical surface, always the characteristic length is the height. Now we move to the top and bottom plate. Okay. For the top and bottom plate, we should go exactly over the same procedure. So what is the first step? The first step is to calculate the Rayleigh number. Okay. To calculate the Rayleigh number, but pay attention, as we said, to calculate Rayleigh, we need characteristic lengths. And the characteristic length is, as we said, the area of surface over the perimeter of the surface. Okay. In general, you have the top and bottom. For the top and bottom surface, it's true that we are doing analysis per unit length, okay? But since it's a very long duct, for a very long duct, what you can do, you can consider your whole duct. And for the characteristic lengths, you take the characteristic lengths of the whole surface. And after, when you want to calculate per unit lengths, you do H bar times area times delta T. You divide then A by L to get Q prime per unit length. But when we want to calculate the characteristic length, you should take it for the whole surface. Okay, should take the characteristic length for the whole surface. And since here the duct is very long, they told us that we have a very long duct. So L is very